So in the last lecture we have seen the equation of the orbit in a central force field, and we have also seen that if there is any body which is moving under the central force field, it will follow the orbital path. Okay, now the motion of the planets in the central force field is governed by the Kepler's laws. So Kepler gave three laws regarding the motion of the planets, and as we know that this gravitational force field is a central force field, and therefore we are dealing with the Kepler's laws which govern the motion of the planets in the central force field. So the Kepler's first law states that every planet moves around the sun with in an elliptical orbit with a sun as its one of the foci. So this is the sun and this is any planet, say Earth. So any planet revolves around the sun with a sun as its one of the foci. So this is the statement of the Kepler's first law. Then Kepler's second law says that area swept by the radius vector drawn from the center of the planet to the center of the sun in equal interval of time is equal. So what is the meaning of this? So suppose this is the sun, this is the earth, and this is a radius vector drawn from the center of the sun to the center of the earth. Okay, so the area swept by this radius vector, okay, suppose this is the time t. Okay, so this is the in time t, this radius vector is moving from this place to this place. Okay, and this is the area swept by this radius vector in time t. Okay, now if this radius vector comes over here in the same time period t, it will move from here to here. Suppose the position of the earth is now here, and in time t now it is moving from this place to this place. Okay, now this is the area swept by the radius vector. Now the second statement of the Kepler's law states that in an equal time period the area swept by the radius vector is equal, which we can say that this dA upon dt is constant. So this is the statement of the second law. And the third law says that, so this is t square proportional to a cube. So the period of the square of the period of the revolution of the planet is directly proportional to the length of the semi-major axis. Length of semi-major So this A is nothing but the length of the semi-major axis. So the period of the revolution square is directly proportional to the cube of the length of the semi-major axis. So this is the statement of the Kepler's third law. Now let us see the proof of the Kepler's first law, which says that every planet revolves around the sun in an elliptical orbit with sun as its one of the foci. In a previous lecture, we have derived the equation of the orbit. So the equation of the orbit was d square u upon d theta square plus u, so which is equal to minus m upon L square u square into f of 1 upon u. This I have written in somewhat different form. So in a previous lecture, so this m upon L square u square was on this side. I have just taken it in on the another side. Now when we are dealing with the gravitational force field, we know that this force is directly proportional to m1 m2 upon r square, which we write it as a, or if you remove this proportionality sign, so this f is given by g m1 m2 upon r square, or I can write it as a k upon r square. So this force is of the type of 1 upon r square. Now we know that this v is nothing but the integration of minus f of r dr, which can be written as integration of minus k upon r square into dr, which is equal to minus k upon r, and it can be written as minus k into u. So we have already seen in a previous lecture. So this 1 upon u is nothing but r, or r is equal to 1 upon u. Okay, so this u is any function which is inversely proportional to this r, which is the definition of the central force field. Okay, now if I take derivation of this dv by dr, or d by dr of minus k into u, so it will be minus k into u square, which is nothing but the f of 1 upon u, or is equal to f of r. So derivative of this term, so that is nothing but minus k into u square. Now just put this value of minus k u square into this equation 1. I will write it as a equation 1. So it will give me d square u upon d theta square plus u is equal to minus m upon L square u square into minus k u square. So this u square will get cancelled, and I am going to get is m k upon L square. So this minus and minus will become plus. So the equation of this orbit will become d square u upon d theta square plus u is equal to mk upon L square. If I take this u on the right hand side, I will get it as minus u. Now so this y is equal to u minus mk upon L square. For the equation to bring in a particular format, so some mathematical adjustments are done over here. Okay, so let this y is equal to u minus mk upon L square. So if I put this value of y into this equation, d square u upon d theta square is equal to minus y, or I can write d square u upon d theta square plus y is equal to 0. So this is a second order differential equation, and the solution of such kind of equation can be written as y is equal to u, or u dash, cos of theta minus theta dash. If we fix our frame at the theta dash, we can write y is equal to u dash cos theta. Okay, so this is the solution of such kind of equation, which is mathematically proven. Okay, now let me put the value of this y. So value of y is u minus mk upon L square, which is equal to u dash cos theta, or u is equal to u dash cos theta plus mk upon L square. So this u is nothing but 1 upon r, so which is equal to u dash cos theta plus mk upon L square. If I take common mk upon L square common from this, so I am going to get 1 plus u dash cos theta upon mk upon L square. So this is the value of 1 upon r. If I take the r, everything will in the denominator will go in the numerator. So it will be L square upon mk into 1 upon this whole term, 1 plus u dash cos theta upon mk upon L square, or I can write it as a L square upon mk divided by 1 plus u dash cos theta upon mk upon L square. So this is the r, and this resembles to the r is equal to p upon 1 plus epsilon cos theta, which is an equation for any conic section which is derived previously from the mathematics. So the conic section could be anything like hyperbola, or it can be parabola, or it can be ellipse, or it can be a circle. So this is the general equation for the conic section. It means that the particle which is entering in the central force field, it will follow some conic section path. Okay, so whatever which we have derived from the equation of the orbit in a central force field, or from the gravitational force field, it resembles to the equation which is derived for the conic section. So this is a proof of the Kepler's first law, which says that so any particle or any body which is moving through the central force field, it will follow some conic section. Okay, now particularly speaking about the Kepler's law regarding to the planet. Okay, so if we can prove this as a ellipse, okay, so that will be the proof of the Kepler's first law. So from these two equations I can write P as L square upon mk, and I can also write epsilon as u dash L square upon mk. From this equation I can write it as a r into 1 plus epsilon cos theta is equal to P, or r plus r epsilon cos theta is equal to P. If I am trying to write this equation in a Cartesian coordinate system, we know that x is equal to r cos theta and y is equal to r sin theta. If I square and add, x square plus y square is equal to r square cos square theta plus r square sin square theta. So x square plus y square is equal to r square, and now this r is equal to square root of x square plus y square. So let us put the value of this r into this equation. So this is nothing but square root of x square plus y square minus plus, so this is r cos theta is nothing but x, so it will be epsilon x is equal to P. If I write it as a x square plus y square square root of is equal to P minus epsilon x, squaring on both sides, we will get x square plus y square is equal to P minus epsilon x bracket square. Now if I expand this bracket, so it will be P square epsilon square x square minus 2p epsilon x square plus y square is equal to, if I take these two terms, so x square into 1 minus epsilon square plus y square plus 2p epsilon x is equal to p square. Okay, so when I put the value of this epsilon as 1 and 0, I will get the different conic sections. Okay, so this is the general equation for the conic section. So let us put the value of epsilon as 1. So if I put here 1, so this term will become 0 and this term will become 2px. So the equation will be y square plus 2px is equal to p square, or where I can write y square is equal to p square minus 2px, so which is the equation of the parabola. Now if I put the value of epsilon is equal to 0, so the equation will be x square plus y square, so this epsilon is equal to 0, so this term will become 0, so which is equal to p square. So this is the equation of the circle. Okay, so we can see that for the different values of epsilon, we can get the different conic sections. Okay, now we remember that we have to prove the statement of the Kepler's first law, which says that so planet revolves around the sun in an elliptical orbit. So let us evaluate for the equation for the elliptical orbit. So the general equation of the orbit is x square 1 minus epsilon naught square plus y square plus 2p epsilon x is equal to p square. This equation I have written above. Okay, and we have derived the equation for the parabola and the circle. Now we have to derive the equation for the ellipse and hyperbola. So for ellipse I can write, if the epsilon naught is greater than 0 and but less than 1, write it here, dividing by 1 minus epsilon naught square. So let me divide it. So it will be x square plus y square upon 1 minus epsilon naught square plus 2p epsilon x upon 1 minus epsilon square is equal to p square upon 1 minus epsilon square. Now let us add the equation by, so p square epsilon square upon 1 minus epsilon square bracket square. Just few mathematical steps to bring it in a form of a ellipse. Okay, so there is no conceptual things are there, just some mathematical adjustments. Okay, so just add this equation by this term. So let me write it as a x square plus y square upon 1 minus epsilon square plus p square epsilon square upon 1 minus epsilon square bracket square plus 2p epsilon x upon 1 minus epsilon square is equal to p square upon 1 minus epsilon square plus p square epsilon square upon 1 minus epsilon square bracket square. Okay, so this x square, so this pex and this, so these are the square of x square plus p epsilon upon 1 minus epsilon square bracket square. Okay, so this is x square plus y square is there, p square e square upon 1 minus epsilon square bracket square multiplied by 2p epsilon x upon 1 minus epsilon square. Okay, so this is nothing but the expansion of a plus b. So what are the remaining terms over here? So y square upon 1 minus epsilon square, so which is equal to p square upon 1 minus epsilon square plus p square epsilon square. So just let multiply this by 1 minus epsilon square, so it will be p square 1 minus epsilon square plus p square epsilon square 1 minus epsilon square bracket square. So let me first write down the right hand side. So it will be p square minus p square epsilon square plus p square epsilon square upon 1 minus epsilon square bracket square. So it will be p square upon 1 minus epsilon square bracket square. So the left hand side will be as it is. So it will be x plus p epsilon 1 minus epsilon square bracket square is there, y square 1 minus epsilon square. So if I divide this whole term by p square and 1 minus epsilon square, So I will write it here. So dividing by, so if I divide this whole term or the whole equation by p square upon 1 minus epsilon square bracket square, so the right hand side will be 1, and this whole term divided by, so this first bracket is there, x plus p epsilon upon 1 minus epsilon bracket square upon p square upon 1 minus epsilon square plus y square upon 1 minus epsilon square divided by p square upon 1 minus epsilon square bracket square. So this is nothing but the form of some x square by a square plus y square by b square is equal to 1. So this is nothing but the equation of the ellipse. So we can say that if the value of this epsilon is greater than 0 and less than 1, so this is the equation for the ellipse. So if you put the equation of the orbit in a central force field, and if you take the value of this epsilon greater than 0 and less than 1, you can say that the planet is revolving around the sun in an elliptical orbit with sun as its one of the foci. Okay, thus we have seen how the motion of the particle in the central force field could be either parabola or circle or ellipse. It can be also hyperbola if this E is greater than, or this epsilon is greater than 1. We just have to divide the same equation by epsilon square minus 1. Okay, so let me divide. So this is x square minus 1 epsilon square plus y square plus 2p epsilon x is equal to p square. So this is the original general equation for the conic section, and if I put this epsilon is greater than 1 for this, just let me divide it by epsilon square minus 1. So for that, what I am doing here is I am taking common x minus from here, so x square into epsilon square minus 1 minus y square minus 2p epsilon x is equal to minus p square, or I'm just taking this common minus sign over here, so the remaining terms will remain as they are. So if I'm dividing it by epsilon square minus 1, so I'm getting x square plus y square upon epsilon square minus 1 plus 2p epsilon x upon epsilon square minus 1 is equal to p square upon epsilon square minus 1. Okay, now same step will be followed over here. We just have to add p square epsilon square, add the term p square epsilon square upon epsilon square minus 1 bracket square. Okay, so it will be x square plus y square upon epsilon square minus 1 plus p square epsilon square minus 1 bracket square plus 2p epsilon x epsilon square minus 1 is equal to p square upon epsilon square minus 1 plus this term p square epsilon square minus 1 bracket square. So this x square, this 2px, and this is the expansion of the bracket 2p epsilon, so it will be expansion of p epsilon upon epsilon square minus 1 minus x bracket square plus y square upon epsilon square minus 1, and the right hand term will be p square epsilon square minus p square plus p square epsilon square upon epsilon square minus 1 bracket square. So this p square epsilon square and this will get cancelled, and what I am going to get here is p square epsilon square minus 1 bracket square. So this term will remain as it is, epsilon square minus 1, and this will be p epsilon square minus 1 minus x bracket square. So if I take the minus term outside of this, so it will be x plus p epsilon x minus p epsilon square minus 1 bracket square. So when I take this minus sign common from this, so I am going to get x minus p epsilon e square minus 1, so this bracket square plus y square epsilon square minus 1 is equal to minus p square epsilon square minus 1 bracket square. So if I want to change the sign of each and every term, so it will be plus, this will be minus, and this will be plus. Now I want this right hand side as equal to 1, so just divide the equation by p square epsilon square minus 1 bracket square. So I have just divided each and every term by this right hand side, and what I get is equal to 1. So this term is equal to 1. Now this is in the form of x square minus a square minus y square by b square is equal to 1. So which is the equation for the hyperbola. So the moral of the story of this equation says that whenever a body enters into the central force field, it will follow the conic section. Okay, so the conic section may be parabola, circle, ellipse or hyperbola. And particularly speaking about the Kepler's laws which govern the motion of the planet in the central force field. The first law says that every planet revolves around the sun with the sun as its one of the foci. So the elliptical orbit equation has been driven here.